Hey, and welcome to Web3, the interconnected web. I'm going to be your host, Dan Nolan, going to be going over this presentation in advance of Shapecraft. If you haven't checked out Shapecraft already, go to Shapecraft. I'll give you a link for it down below, so check it out. Go to this hackathon. It's the first Alchemy University hosted hackathon. We're super excited about it. It's going to start on November 18th, and there's going to be $250,000 in prizes for folks like you that can be creators, developers on this ecosystem. What I want to do today is I want to sort of reintroduce the concept of Web3. So for folks of you who already know Web3, some of this may be review, but I want to kind of reframe the way we think about Web3, at least maybe for this particular use case, for this particular hackathon. And for folks that are brand new to Web3, brand new to crypto, this is going to be a good place to start to understand what these things are, how they work together, and kind of go from there. So super excited to dive in with you here, and we'll get started. So let me go ahead and present, and we will jump in here. So I will share screen, and let's do this one here. Okay, cool. The infinite window. All right, cool. So today we're going to be talking about Web3, the interconnected web. So this was a new sort of way that I wanted to think about Web3 and a new way to reframe it for the Shapecraft hackathon. So so let's go ahead and just dive into this. So to start off from, like I was saying, I want to start from the very beginning and think about blockchains, reframe Web3 a little bit from the get-go. So for blockchains, the purpose of a blockchain, when we think about it, is that we can decentralize where state lives, code runs, and we can all agree on an output. So if you're unfamiliar with the concept of the blockchain, you can sort of just think about it as a server, but a place that we can put code and state. Maybe you have a server and a database, but we can all agree on the output. There's a consensus on the output. We have one place that we can look at for the source of truth, right? So as we go down this presentation, and I promise you we're going to get to the more interesting stuff in a moment, I'm going to be talking about different code architectures for how we can combine servers with blockchains in a way where we could start to think about the trust assumptions and where that actually may be useful to have some code running on server, some state running on a server, and some code and state running on a blockchain, right? So for a blockchain, we know we could put this code and state and we all agree on the output. It's deterministic. We know what goes in. We know what's going to come out when we do that. And there's no single owner of any particular code's execution. Now, when we talk about smart contracts in a moment, developers can choose to write their own privileged code. So you can say that only some people can write this code here. Only some people can write to the smart contract. Only certain people can do certain things within the smart contract's execution. You could program in privileges, but by default, there is no single owner of the code's execution, and the code is always run as programmed, and it's transparently verifiable. So a question that I love to pose when we're going back to blockchains is taking a look at this piece of code here and asking, is this code decentralized, right? Decentralization is a big word that people love to throw out in the blockchain Web3 space. And when you're looking at this piece of code, you may say to me, Dan, I know that's Solidity, and Solidity typically runs on EVM chains, and EVM chains will be decentralized. So in that case, the code is decentralized. But the point I want to make here is the code itself isn't decentralized, right? It's where the code runs, what the chain is doing, how many nodes in the network are running that chain, whether it's settling to a layer 1 chain and what layer 1 chain that is. All of those sorts of things come in. It's where the execution is happening that makes code decentralized. So code decentralization, you can imagine taking that code and putting it on a bunch of different servers. So before we get to the idea of blockchain, you could just think of taking a bunch of different computers and just putting code on all of those different computers, and maybe some state too, right? If we had something like this, where each one of these computers could do like a balance check and could like change the balances for different people talking to these different computers, you could imagine this code being decentralized in such a way that you could talk to any of these computers and get the same functionality. Now, of course, this doesn't really do anything for us, right? So if you had 6 computers that all had balances on them, that doesn't really do anything because there's no source of truth, right? There's no one place that you can go to and say, what's my balance, right? Unless these 6 computers are, interacting in some way such that we know that they are definitely agreeing upon one source of truth. And one way you could do that is you could like regulate it, right? You could have legality built around these entities that are running these servers, kind of like banks, right? Where you could actually make sure that these banks are doing exactly what they said they were supposed to do, and they're maintaining APIs to communicate with each other and update each other's balances through a clearinghouse. But when we talk about blockchains, we take this and we actually create a protocol such that these things happen via the rules of a transparent protocol. So the blockchain network comes in and introduces this idea that you can have a whole bunch of machines, a whole bunch of nodes, and the network will run the code as it's written. The blockchain enforces these rules. So when a program is enforced, it is called a smart contract. And we're going to talk about smart contracts a little bit further on. I want to first kind of just touch on this idea of blockchain just to sort of underlie the conversation. I think it's going to be really important as we start to talk about this idea of Web3 being the internet connected web, and this idea of being able to build partially offline, partially on-chain, partially off-chain applications. So Bitcoin was the first successful blockchain. Bitcoin was the first successful cryptocurrency. But before Bitcoin, there was much research and many attempts to create something very similar to it. Bitcoin was the first one to really put together some key components that were already discovered, some cryptography that we're going to talk about, some things we're not going to talk about. But most of these components were already discovered before Bitcoin came along, and Satoshi lined them up in a way such that Bitcoin was able to just move forward and be the successful network that it is today. So some of the components that I just want to key in on today, again, to underlie this conversation, is public key cryptography, proof of work, and this longest chain rule. So really quick from the top for these three different things. With public key cryptography, this may be a little bit different. If you're coming from a web application development background, you may be familiar with like storing passwords in a database and doing like login via like email password, right? Like the traditional way that we think of web application authentication. There's many different ways of doing authentication, public key cryptography being one of those different ways of doing it. The cool thing about public key cryptography, and we'll talk about this in a moment, is you could actually have authentication without storing secret info. So you actually keep the secret info on the client, on the user side. That's why we have in Web3, you think about private keys that you need to keep safe. And then on the server, it could just verify with mathematics, with like an elliptic curve, that that is indeed the person who signed that transaction or signed that message, right? So public key cryptography is going to be a really heavy lifter in what we're going to be talking about here. Also, proof of work. So also we're not going to be talking about proof of stake here today, but like a consensus mechanism that allows us to have a network that can agree upon a common state. The reason why I wanted to highlight proof of work is it's really easy to understand, and I'll show you that in just a moment. And it's where it all started from. So I think it's a really good starting point. And then the longest chain rule is going to be this idea that we can focus on one place, and we know that everyone's focus is there. Why do we know that everyone's focus is there? Why is that the source of truth? Because most of the work is done on that chain, because the longest chain has the most work done on it, because via the proof of work mechanism that we'll see in a moment, you have to do a whole lot of hashing in order to create a longer chain. So just by seeing a longer chain, the ability to look at a chain and say, hey, this one's longer than your chain, I know that more resources have been spent on this one. That creates a point that we can all focus on. That creates a consensus. We can all say, instead of this picture over here where we have many different computers all keeping track of their own balances, we can actually say there's a longest chain out there, the one where most of the resources are focused on, and we can go ahead and focus on that particular one. This is often called a very elegant solution to what's called the Byzantine generals problem, where you have a bunch of Byzantine generals who are trying to figure out when to attack, and they can't coordinate to figure out the right time to do it, right? Some leave, some attack at a different time. But if you have a bunch of decentralized sort of entities that need to collaborate together, something like this with the longest chain rule is going to give you that consensus of saying, this is where we are going to focus. So let me just talk about these things really quick before we talk about Web3 a little bit more broadly, and server architecture, and how you can think about blockchains as opposed to a server or a database, and how you can fit it all into your web application, game, app, whatever. So let's go ahead and jump in here. So for crypto, crypto is this term that's actually existed long before cryptocurrency. So today we talk about crypto. We are generally referring to cryptocurrency, but of course there's also cryptography, right? There's cryptographic hash and there's public key cryptography. These are things that underlie all the things that we're seeing in cryptocurrency today. So cryptographic hash is going to be the first thing that I really want to focus in on, just to give you an understanding of how proof of work works, but also because if you're coming into this space, cryptographic hashes is something you're going to see all over the place because it has a number of important properties that are going to make it really, really useful for blockchains and systems that interact with blockchains. So for a hash function, what a hash function is it's something that you can give me an input, big or small, and I'll give you a fixed size output. So your input could be any type of data. It could be a number, it could be a string, it could be an image, a video, something really, really, really large, and you put it through this little filter, right? These little blue filters is like the hash function, and you get something out the other side. Now, these little blue filters are a good example, like a good sort of image to encapsulate what a hash function is doing. We don't know what's going on inside of the blue filter. We don't have an idea of what's going to come out the other side. We just know that it's doing some bit shifting, it's doing some mathematics, and then something else is going to come out the other end. The only way to know what's going to come out the other end is to actually run the hash function and then see the actual result, the actual output. So the hash function has some really important properties. It's deterministic. And what that means is when you put in the Mona Lisa image right here, as long as that has the exact same data as another Mona Lisa image, you're always going to get that hash out, 0x7cDE. That hash is always going to come out. You're always going to get the same one, putting it through the same hash function. That's really important because if you're talking about a big piece of data and you want to agree on that piece of data, the hash can be representative of that piece of data, right? It is also pseudo-random, and by pseudo-random, that means that property that I was talking about, where you don't know what's going to come out of the hash function until you actually run the hash function. You have the end result. You take a look at it, it looks nothing like something very similar. So if I were to, this SHA-256 is one such function that provides a 256-bit output. It is a hash function, and pseudo-random is best described taking a look at it if we were to put in some inputs. So if I were to put in the input ABC, if you can see here, ABC spits out this output right here. This is the hash. No matter when you run this, if you run this on your machine, you go search for SHA-256 online and you put in ABC. No matter when you run this, 10 years from now, it should always come out. SHA-256 should always calculate this exact same output, right? It's deterministic. That's that rule. It's also pseudo-random. So if I were to put in D here, A, B, C, D, I'm going to get a completely different output, right? I don't know what that's going to look like. It's not going to look anything like this. I mean, it might, right? It's pseudo-random. I have no idea. It could look almost identical, but the chances are it's going to look extremely different when I type D here, and it does. It looks very different, right? 88 is the start there, as opposed to ABC is a very, very different output. That's an important property of these deterministic or these hash functions here as well. It's one way. In other words, you can go one way, but you can't go back the other. I can't take this hash output and figure out what the input was unless I already know the input, right? There's an idea of a rainbow table where you already know a bunch of common inputs to a hash function, in which case you could know that this output relates to this input, but without actually going through and trying a bunch of different inputs, if you don't know the input, you have no way of getting there besides brute force. Another really important property of hash functions is they are fast to compute. And so you can see here that I'm running it, and it's very, very fast to go from input to output. And then the last thing is they're collision resistant. So if I have another input like A, B, C, D, E, F, G, H, it should be very hard to find an output, especially for a 256-bit output. So something like this should be impossible to find an output that's the same for two different inputs. And as far as I know, SHA-256 doesn't have any collisions that are heard of. If you sort of restrict the output space so that you have a much smaller output, you can find collisions, right? If we were only focused on the first 8 bits here, we could potentially, or the first 8 hexadecimal characters here, we could potentially find some collisions. But if you were focused on the whole thing, it's going to be really, really, really hard to do that. Okay, cool. So that is cryptographic hash functions. The reason why I bring those up is because they are core to this idea of proof of work. And proof of work was the first thing that I wanted to talk about here. Proof of work is this idea that you can have many machines that are all trying to come up with a consensus on an output. And what you do with these machines in Bitcoin's particular case is you have some kind of input that's a block. It's a series of transactions that's trying to write to a database. So if you're thinking about databases from Web2, that's, a really good analogy there, right? We're trying to write to an actual data source or data destination inside of the chain data on the particular blockchain node that all the blockchain nodes are going to agree upon. So what you're trying to do is you're trying to do like transaction, we'll have like a set of transactions. So this input is going to look like JSON. That's just how I'm going to format it, I think, in JSON most of the time. So transactions might be like Bob sends Alice 20 Bitcoin. That's a lot of Bitcoin, Bob. What are you doing? Charlie sends Alice 1 Bitcoin, sort of like this, right? And so what Bitcoin might do as a rule is say, hey, in order for you guys to get these transactions through, it'll say to the miners, what you're going to have to do is you're going to have to come out with an output that has a bunch of leading zeros. And the more leading zeros you have, it's going to be harder and harder to find an output that actually makes this a valid block. So this would be a block. It's a series of transactions. It's a series of state changes. If you want to think about it like that, we're going to be talking about smart contracts where maybe the state is not necessarily like sending Bitcoin or Ether from one transaction to another, from one user to another, but really like some sort of state change, like maybe Charlie posts to a social network, right? That could be a transaction potentially in a smart contract network where you are trying to do posts, you're trying to do other things, you're trying to mint NFTs, you're trying to do other things like that. So you could have many transactions. And what Bitcoin miners do, and what miners do in general for proof of work, is they will take this and they will try to come up with a block such that they get that output with 2 leading zeros. So what they'll do is they'll increment a nonce and maybe some other data inside of the block until eventually they come up with an output that has those 2 leading zeros. So that might take me a while. Technically, on average, that would take like 256 tries. I might just try for 1 leading zero here and see how long it takes me to do. So here I'm mining. This is mining, right? I'm trying to mine myself an output where I'm trying to come up with a leading zero. There we go. I got to nonce 11. It may have taken me a lot longer to get to 2 zeros and a heck of a lot longer to get to 3 zeros, right? Because every time that you're trying to get 1 more zero, the probability of getting 3 zeros in a row is hexadecimal has 16 characters. So you actually need to multiply 1/16 times 1/16 times 1/16. So we're getting exponentially harder every time that we add in a leading zero. If you take a look at like Bitcoin blocks, you'll see that there's many, many leading zeros, right? This is what mining is doing, is it's coming up with this proof of work such that when a block is mined, a whole lot of resources were spent coming up with that block, right? And we could say that most people in the world, most miners are focused on this particular chain, and we're saying this is where all the resources are spent. Somebody could come along to you and could say, or to me, right, and be like, hey, Dan, here's the longest chain. It has, 12,000 blocks. And I could be like, no, I know that somebody else told me that there's a longest chain that has 12,001 blocks. And I know that that's the source of truth because that's where most of the resources are focused. So you can't get me to believe that your blockchain that's smaller is where everyone is focused. You can't get me to believe that that's the source of truth. I know without a doubt the longest chain is the one that wins. That's how we can get consensus in a blockchain, right? So it's core that we understand hash functions in order to understand that idea of consensus. Proof of work is going to be the most simple way of thinking about how do we get a source of truth. And the hash function is absolutely critical to that, the whole mining idea. Now, of course, there's proof of stake, which we're going to see in a lot of smart contract chains today. And that is another way of coming up with consensus as well. I'm not going to dive into that here because it's not as straightforward. It's not as simple. There's a lot of things that need to be thought about there. but it does function in the same way that we can come up with a consensus on what the state of the network is. Great. So the other piece of crypto that I want to talk about here, just to sort of underlie the concept, once again, we won't go too deep into it, but if you like stuff like this, go to Alchemy University. You could go to alchemy.com/university. There's a whole bunch of other great resources on this stuff where I can spend a lot more time diving into these different concepts. But just as an overview, let's talk about public key cryptography. So before we get into public key cryptography, I just want to talk about cryptography, just like symmetric key cryptography. So this is a common term. So public key cryptography is typically called asymmetric key cryptography. So symmetric key, what it means is there's the same key on both sides. It's the same, right? When you think of symmetry, it's the same on both sides, right? If I have good face symmetry, then my left looks my right side of the face, right? For a symmetric key, you have the same key on both sides. That's why I colored it blue, both sides here of the transaction. Symmetric key cryptography was the first type of cryptography that was really used, especially in like military purposes, like, I don't know, dating back to like Roman times, right? Caesar famously had like the Caesar cipher, which is kind of similar to what you see here, where you could take a message like hello world and you can encrypt it by shifting every single character over by one, let's say. So hello world becomes IFMMP, XPSME, because you take H, you shift it over one to I, you take E, you shift it over one to F, LL over to M, right? That's not super great because you could see that even in my encrypted message here, there's three M's, right? There's three M's. So one thing that you could do as somebody who gets this encrypted message is you could say, M is a very common letter in your message. That seems like maybe it's a really common letter in the English language. And then you could start to deduce maybe what these letters actually are. And if you get it right, then you have the entire thing unencrypted because it's only a shift by one, right? A better way to do it would be a much longer key where you have something maybe that's as long as a message, right? So you have a cat and you're going to shift C by 3, A by 2, and T by 4, right? You're kind of applying that key to the message and you get FCX. That would be really hard to unencrypt. Virtually impossible, right? Because even if you guess one letter, and I don't know how you would really, how would you guess another? There's no, the key is different for every single character. So that would be extremely hard to unencrypt that particular message, right? So really long key is going to be something that is going to be ridiculously hard to unencrypt on that side. So the downside of symmetric key cryptography is, for example, for Bob and Alice down here, they both have to have the same key beforehand. So for the internet, that doesn't work super well. If I've never met you over the internet and we want to communicate securely, just not going to work, right? I can't get you my key. I got to meet you up in person and then we can hand keys off like they did for PGP. We could do something like that, right? But, you can't do that over the internet just with anybody that you happen to meet, right? So symmetric key has its usages, but it's not going to be something that, is going to be good for strangers across the internet. So there's this idea of asymmetric key, which, as you can guess, is going to be two different keys. It's going to be the blue and the pink key, where you have one that's actually called a private key and one that's called a public key. So you may be familiar with this term of private key in the Web3 space, and a public key you probably more commonly see as an address, right? There's an algorithm where a public key can go to an address. So it's not quite the same, not quite one-to-one, but you can think of it as an address, right? So the private key is going to be the thing you want to keep secure. Don't tell anyone your private key. Public key is going to be the thing that identifies you, and these keys have a mathematical property that links them together. So asymmetric key, where the keys are different, is called public key cryptography. And this is the key idea behind what we can do with authentication on a blockchain network, because what you can do is you can secure your private key, which is going to be the pink key in this case, right? Bob provides his public key to everyone. So everyone knows that if you can use this public key to mathematically link it to the message, you know that Bob signed it somewhere with the private key because Bob said, this is the public key that represents me. And everyone could do a mathematical calculation such that they know that this could have only been signed by Bob, right? That's why like everyone talks about Satoshi. And if Satoshi ever wanted to reveal their identity, they could just sign a message, right? And we would say, oh, wow, that's Satoshi's message because that's the same key that was used to, sign a block or something, sign a transaction from back in those early days of Bitcoin mining. And so there could be cryptographic proof of somebody with the keys that Satoshi had, right? So in this particular case, Bob signs with the private key. You get the message that this is from Bob, and everyone here can agree that that's Bob's public key. So in Web3, this might look more like this, right? Where you have a private key, maybe in a browser extension. You have it like up in MetaMask, and you're signing with a private key. You send it over to a bunch of computers. They recover the public key from the signature, and the address is derived from that public key. So your public key to address could be something like this, where you have a public key that's 64 bytes long. The key is you put through a one-way hash called Ketchak 256, and this produces a 32-byte output. Last 20 bytes are used for an address. So you might have a public key that makes this address, and you've probably seen this sort of thing on Etherscan before if you've used EVM chains, if you've used Etherscan, if you've used anything like this, right? You would see a block explorer, and you might go looking for your address to see what kind of transactions are related there, what kind of assets you hold, that sort of thing. So that's public private key cryptography. So we touched on all of these core components. I think it's important that I give you this background before we dive into what I'm going to talk about next, which is Web3 as this interconnected web. So the core components: public key cryptography, proof of work, longest chain rule. Public key cryptography is a heavy lifter for blockchains because it gives us that ability to authenticate somebody without storing secret info on the server, right? If you do traditional web-based authentication where you have a password and an email, it's up to you as a developer to hide the password somewhere in a database. Now, ideally you hash it, right? And you have like good security set up. So maybe you have a salt somewhere or whatever, like you figure out some way of matching up the passwords where you're not just storing plain text passwords. If you're familiar with all of that, then you've probably done some authentication in the past. If you're not, don't worry. But that's kind of like, if you've ever signed in with an email and a password, there's stuff that has to happen on the back end where it's making sure that your password is indeed the password for that email address, right? So there's secret info on the server somewhere. For blockchains, we can't have that because they're all public, right? Anyone can run a blockchain node. It's permissionless. So you can't just like say, oh, you want to run a blockchain node? Here's a database with all the passwords of everybody who wants to interact with the network, right? So you need public key cryptography for that sort of thing. You also need this ability to concede. No, you want to come to consensus on a common state. And that's where proof of work and longest chain come in, because when you do proof of work, you have this ability to say all these miners use some amount of hashing power to come up with this block. And so therefore, when you look at the longest chain, we know without a doubt, there it is. That's the one that everyone's focused on. That's our Schelling point. That is the solution to the Byzantine generals problem, right? There's a consensus algorithm. So when you hear consensus algorithms, you can think of proof of work. You can come back to this, visit how it works, and then you don't have to worry about it. You could just understand that like any other consensus algorithm also does the same thing. We want to come to an agreement upon the state of the network, right? But may do that in a different way that has different properties. Cool. So the interconnected web, right? How do we get here? Why is this the title of the presentation today? So the interconnected web. So taking a step back, a little bit here, I want to just talk about what it would look like to have some data on a server, right? So this is traditionally how you might think about doing, a database and some code on a server where you're storing people's balances. And maybe these balances aren't, real balances, money. Maybe it's just some like fake currency, virtual currency within a game that's not even like super important. Maybe it's like play money in a poker game that nobody, has any value associated to it, right? You could have a server that allows people to transfer that to a different account, and you could keep track of when somebody loses money in the poker game so that they could like transfer it over to somebody else. And maybe you trust the server to do this because it's just your play balance. You don't care if they change the amount, then whatever, like maybe they ruined your day because you were playing and then they changed your balance, but it's not actually like taking money out of your account, something like that, right? So on a server, you could do something like this. You have a database, you have some code, allow people to transfer and change their balances. And you could imagine that if you had something like this where people could transfer and change balances, you could imagine that other people would want to plug into it, right? And they might say, hey, you have that poker server. I want to build on top of that poker server. Maybe I want to create like tournaments. I want to create a tournaments client on top of your poker server such that, I can arrange tournaments and people could actually like play these massive tournaments, poker style, whatever. And they might build an entire company on top of your business, on top of your server right here, right? But of course, we know that, especially so if it's just play money, then maybe the amount doesn't matter. If it's not play money, then this is a big problem, right? Because you have one computer that can change the amounts in the database. You have one computer that can change the code. You have one computer, one server that can revoke access to the API. So whether this is play money in poker and you build your entire business around it, or whether this is an actual like financial application, it's not something you want to just entrust to just any given server, right? And you don't want to build your business on it. So all of these computers on the side here might be somebody who's starting a business on top of your machine, and say, I don't think I want to do that, because there's been precedents in the past where you have somebody building a big network, a big game, a big social network, something to do with money. People build businesses on top of it. And unfortunately, you're not building on a solid foundation there, right? Because in all these cases, they could just change the data. They could change the rules. They could revoke service or charge you for that access to the API, because they've built up a huge network that now, if you want to have access to their users, you got to pay for it, right? And this makes sense from the business models of the things that need to run in these cases. But it's not something that you could build businesses on top of. So when I'm thinking about the interconnected web, it's thinking about a web that you can actually build a business on top of and have some trust, right? Have some trust that it's going to continue to run. So you might build your business on top of something where that same code, that same data is in a smart contract on a blockchain. Now, I didn't really touch on smart contracts too much because when we talked about Bitcoin, but you could just think of them as program, as code on a blockchain. So any arbitrary code that you want to have a blockchain, you write the code, you deploy it to a blockchain, and then you could have some storage or the data, the database that lives on the blockchain, some state and some code, right? We could build a business on top of this, and many people have, where you can actually just rewrite to the chain, and you can look at the code and say, that's how it's always going to behave, right? Now, it's difficult to build a business starting from something like this. So very often you want to add more code on chain for any updates or integrations, things like that. If you have a complex enough, smart contract, you're going to want to be able to make upgrades. You're going to want to be able to do integrations. You're going to want to be able to do other things, right? And so a lot of folks have worked on smart contracts that can upgrade with, novel governance patterns and different ways that you can like integrate with other smart contracts. This right here could be the interconnected web, right? This right here has, the ability to do that. And we've seen that, right? Like if you've used DeFi, if you use payment applications, if you've used Uniswap, you can go to these different places and you could still have the same balance in your account, and you can interact with them, and you could be able to swap, or you could be able to lend or borrow, whatever these sorts of actions are that you're doing in the DeFi ecosystem. And you could think of many different clients interacting with these codes that may just look a little different, right? But at the end of the day, they may be interacting with the same smart contracts. This is a fully on-chain version of what we're talking about here, right? The interconnected web, where all these different clients can then talk to the smart contracts, and we all have one source of truth that's all on chain. One thing I would like to think about, especially going into the Shapecraft hackathon, is how do you create something that may not be fully on chain? Because when you think about games, for example, right? If you think about things that need to do a lot of state tracking, so for games, right, if you have a player who is in a position in the game and they want to move around, like you have a controller and you want to move around the map, and every time that you want to move or you want to do something like interesting in the game has to go and write a transaction to the blockchain. That would be pretty terrible, even on the fastest chains, because it takes a while and it costs money to write to the chain, right? You would have a lag and you would have a cost. And that's something that's very, very hard to hide behind a business model for any company, right? And I think it's a big part of why it's been difficult to sort of create these sorts of games. Now, I do think there are some really great fully on-chain games, and Dark Forest is my favorite example of one. They just did a phenomenal job of creating something that works within a blockchain ecosystem that's novel, engaging, and just super, super fun. And if they still host the servers, it's been a little while since I've gone in there. I would definitely recommend checking it out. Maybe you'll find some gameplay on YouTube. You could see what it was all about. For that, you can imagine all of the game logic and all of the data living on a chain, right? This green box here is the chain that we are trying to interact with. And you can imagine all that stuff being there. But if you're thinking about a more interactive game, it's really hard to imagine being able to read write to a chain that quickly. You know, regardless of all the things that we're going to make improvements on at the L1 level, at the L2 level, it's going to be really, really hard to imagine a scenario where it makes sense to write to a blockchain every time that a character moves like one pixel on a screen. And if you want to do any sort of like checking that the player is any validating that the player's not cheating, you kind of need to know where in the world they are, right? Because did they kill that monster? I don't know. You know, like they could have only killed that monster if they were right next to them and they were attacking that monster. We need to know everything that's going on in the game in order to be able to say, like, did this person cheat or not? And if you want anything of value, you need to be able to like reward those circumstances, those things that those players do with something that you know is cheat proof, right? You know, something that like is validated, right? You want to make sure that that is actually undergoing something that otherwise, you know, it doesn't need to be, those items don't need to be of value. And, you know, potentially then they don't necessarily need to be on chain, right? Like, again, like maybe that test poker money where you're just playing a poker game that like nobody's keeping track of the value because you don't care. It's just all play money, whatever. Maybe that doesn't need to be on chain. I mean, there is a scenario where you can imagine people building businesses on it, and you would want those things to be on chain. So in that case, like building businesses on it, that might make sense. But you can kind of see what I'm saying, right? Like there's an important thing to want some value for these things that are on chain, but you might want to take some of these things off chain. So an interesting thing to point out here in this fully on chain architecture is these clients over here in the bottom left. They could all look a little bit different, but behave the same because you're interacting with game logic and game state that's all on chain, right? So the game is actually being played on chain, but you could load up many different clients to make the game look a little different, right? This has actually happened with a lot of famous games, RuneScape and World of Warcraft. You could like load up a different client, which may have different ways of like viewing it, and may make the game a little bit better. But realistically, the state and the game logic remains the same, right? So you could think of it that way for fully on-chain games. All of the game is being played on-chain. So anytime that the state changes, it costs money, and chains are going to naturally be slower than servers, however much you scale them up, right? That's just the property of chains. And so, you know, it's difficult to build a truly interactive game on chain like this. So something I'd love to see a lot more of is this idea of like partially on chain games and thinking about the trade-offs of what it means to have a game that's partially on chain and partially off chain, right? So if you have a game, and we kind of already do this, right? So if you're somebody in the Web3 ecosystem and you have NFTs, you have you collect a whole bunch of NFTs throughout these different ecosystems, you may already have items that you treasure, that you keep secure, and those are your resources, right? You can imagine games sprouting up that start to use those resources and allow you to take, you know, whatever NFT you have and bring it into those different worlds. However, we haven't seen too much of that yet, and I have a theory as to why that I'd love to explore with you all, especially as we go into the Shapecraft Hackathon. So we kind of already have this with NFTs where you have resources. The resource logic lives on chain, right? And by resource logic, I mean like minting. So if you want to mint a new one, all of that logic is transparent. Maybe people are selling it. Maybe there's you know, a way to mint it that you have to like earn it somehow, right? All of that logic can be written on chain, but the games themselves, which are now these orange boxes, they may have their own server logic that allows you to play a different game with each one of these NFTs, right? So you could have a totally different world that you bring your NFT into and say, I want to play my NFT in this one. I want to play my NFT in this one. So why aren't these games doing this, right? Why aren't games implementing the NFTs? Why aren't games coming up like big games and saying, oh, we're going to implement your NFT collection and bring it into this world so that you can bring your NFTs everywhere? So it might look something like this, right? Where like DeepL, is created by DK, awesome project on the Shape ecosystem. You could bring your avatar everywhere. So these could be very different games, very different experiences that you could bring the same avatar to. And maybe it's not the same avatar, maybe it's not the same character, maybe it's the same sword, maybe it's your same experience points. Maybe it's an item that sort of changes the experience of that particular world in an interesting way, gives you a new unlockable character, gives you a new unlockable move, all those types of things where you could like take it across all these different worlds, I think would make for an extremely interesting user experience, an extremely interesting player experience that we don't see anywhere else because of this problem where you can't build upon APIs, right? We don't have like that single source of truth that we can coalesce on. And there's also another problem here, right? Which is that these are independent games, each one of these orange boxes, but they don't necessarily have like an incentive to work together. And when you take a look at the games, apps, and sites that we may have used that have gotten really popular over time, there's plenty of precedents for wanting to close down the doors, right? Like, a popular one would be like Zynga being built on top of Facebook and having Farmville growing to like a massive user base overnight. And then eventually it didn't become part of Facebook's business model to want all that on their site, right? Inside of the application itself. And so at that point, that game was no longer welcome and no longer fit on the Facebook site, right? So it doesn't make sense to build your games, build your apps on top of these ecosystems that may eventually become closed. But imagine if we were starting from scratch and we all wanted to create a bunch of games, apps, and sites that all collaborated together. What would we want to see? I think we would want to see some sort of an incentive such that these games know that they will get paid when a player moves the items from world to world, right? Moves these people from world to world, such that when you create an interesting world and I create an interesting world, I say, I want to open my player base up to you because I know that we both have an incentive to work together. And you can imagine that working in the long run, where maybe I end up creating a game that is a really popular game and has a massive user base. And in the long run, I recognize that most of the value, most of the monetization of my game comes from payments from other people collaborating with, or people coming from other worlds because I collaborated with them, right? If we realign the incentives, very much like how Bitcoin provided the incentive for people to run miners, peers in a network to actually collaborate together and actually like host this financial system, if we realign the incentives such that game developers, app developers, site developers all have a reason to collaborate together, I think you can get something more like this interconnected web where we actually have games and servers that know that at the end of the day, if they collaborate, they're that's in their best interest. And I think that builds really interesting player experiences. It's something I'd like to explore more with you. It's something I'll be putting out more content on. So if this is super interesting to you, have a couple call to actions. One, if this was interesting to you and you want to learn more about Web3, go to Alchemy University. You can look it up in Google or do alchemy.com/university. If Shape and Shapecraft is super interesting to you, go to shape.network/Shapecraft. Check out everything there. Go into the Shape Discord. Talk about these ideas. Tell me what you think. Tell me if you thought that this was great. Tell me if you think this was terrible. Push back on the idea. I'd love to hear from you. And if you are really interested in game development and you have no game development experience, be hosting another one of these tomorrow, a workshop on building a multiplayer online world, something that you could imagine collaborating with other multiplayer online worlds to build something very much like this. So hope you enjoyed this workshop and have a good rest of your day.